Welcome to the Mei Distinguished Seminar, where we're fortunate enough to host today Dr. Wei Chen, who's the Wilson Cook Professor in Engineering Design and the Chair of the Department of Mechanical Engineering at Northwestern University. Among Dr. Chen's many accomplishments is that she's currently serving as the Design Thrust Lead for the newly funded NSF Engineering Research Center on Hybrid Autonomous Manufacturing, moving from evolution to revolution. And I think, nonetheless, as an even bigger feat, she's an elected member of the National Academy of Engineering. She serves as the editor-in-chief of the ASME Journal of Mechanical Design, the chair of the ASME Design Engineering Division, and until recently as president of the International Society of Structural and Multidisciplinary Optimization. She's received numerous awards and medals, including the 2022 Engineering Science Medal from the Society of Engineering Sciences, several medals from ASME, including the Pi Tau Sigma Charles Russ Richards Memorial Award, the Design Automation Award, Intelligent Optimization Prize, and the Pi Tau, oh that's a lot of Greek letters, Pi Tau Sigma Gold Medal Achievement Award. Please join me in giving a very warm welcome to Dr. Wei Chen. Thank you.
I feel extremely honored to be invited for this seminar. I heard some story about Professor Cici Mate, and it's really an honor to be invited. And I also like to thank all the colleagues here to come over this Friday afternoon. I know that you're going to, there's a long weekend ahead of you. So you can go away and enjoy some other things. So I'd like to share with you today, using the time I have, this topic of data-driven computational design of engineered material system. So I put the word engineered there, really try to emphasize that the engineers can make a large impact on the society by designing and manufacturing, we call artificial systems. And on the other hand, the living system, like nature and the biological system, are also made by materials, right? So design engineering material, actually, lots of the work here is inspired by the characteristic of the system in the living material system. So I like to use this picture here. It's a tale of the two birds. On the left, you can see is it's artwork created by a Chinese artist. I'm trying to use this picture to explain some of the differences between the artificial system, the engineered system versus the living system. So on the other hand, on the left hand, what you can see is that this is a big artwork that is actually made by the construction debris. I know I'm visiting civil engineering departments. I'm trying to include some civil kind of oriented examples here. So you can see that the crest texture is made by the helmet, a little helmet, and then the feather, the body is made by the spade. But in general, what you can see here is that the engineering system largely will focus on more like homogeneous system at the microscopic level, right? And also most of this problem, we call them a more deterministic kind of problem. But on the right is the living system. And if you can look at deeper into the feather of the bird, what you see here are mostly those we call the microstructure that are made by this kind of, we call it this hollow lattice type, right, structure here. First thing you see is that they're very stochastic. It's kind of heterogeneous, but there's some pattern. We call it quasi-random structure. One nice thing about this kind of structure is that they actually can reduce the weight significantly, right? And on the top, you can see that the color of a bird, like with the blue or green, they're actually not by painting, right? On the left, you paint the color. On the right is actually accomplished by the spectral structure. So structure here determines really the property. okay? And those systems are very stochastic. So engineering, designing the engineering material system, I think there's a big group of people, actually Professor Marcus Buller here is very well known for biologically inspired design. And on the other hand, I think one of the goals of designing material system is to manipulate the structure and also composition, try to achieve we call unprecedented performance and property that you never seen, even in the living system. So that is really the center of my talk today, is what are the design methods can accomplish that. So I'm including a few examples here to show you what we mean by advanced material system. And advanced material systems are basically those that are designed by changing the material composition as well as the architecture. And I'm using two examples here. There's several examples here, but the middle one is the right one here, actually done by the faculty, mechanical engineering faculty here. Like in the middle one is Professor Carlos Portela's group, right? They did this lattice structure that can have the supersonic impact resistance. Basically, the architecture is made in the way that can absorb the energy in the high speed. So this is great for defense kind of application. On the right, you see a example from Professor Xuanhe Zhao's group that this is a magnetic wiring system that can be controlled by external magnetic fields to accomplish, in this case, is the surgical. It's related to heart surgery. So based on who is the patient, this kind of image can directly guide the doctor to kind of manipulate the control, the stimuli, so that they can do the right job in the surgical process. And on the left is an additive manufacturing example that use 3D printing to make the battery. So all these problems involve design question and the design challenges. So these kind of problems are very interdisciplinary and or multidisciplinary. And here I show you here the more like a research portfolio of my group during the past decade. I started this research almost a decade ago. And before that, my research was mainly focused on design under uncertainty. And Professor Shearing was asking me, like, how did you get into this field? Is that because your colleague in material science? Indeed, we have a great material science department at Northwestern, and we also have great people in mechanics and also manufacturing. And this collection of the portfolio here actually, I think, is working, collaborating with almost more than a dozen faculty at Northwestern and also beyond the Northwestern. So on the left, what you see are the examples we worked on we call the design D material. So that includes problems like microelectronics material, polymer, MOF structure, and also like a nanopolymer composite. I put them in the different location just to see that, just kind of show that the physical phenomenon, the importance are at a different scale level. For example, microelectronics, the atomic scale design behavior is really, really critical. So moving up, you go to micro and then mesoscale. That's then the macro scale on the right is usually we call design with the material, right? Design with the material are the things that mechanical engineer usually do, right? They're given the material, they try to play with the topology, the geometrical design to accomplish certain behavior. But these days, there's actually the boundary between these two are becoming blur, I would say. And we're actually facing a lot of issues is we need to bring these two sides together. So how do you do concurrent material and architecture design? It becomes more and more critical. But in general, we are taking we call the physics-based approach, addressing this problem, simulation-based approach. So this is a tribute to my colleague, Greg Olson, that he wrote this paper that was back to 1997. He generalized the material problem into really a cause-effect relation, or understanding the cause-effect relation between processing to structure, then to property, and then to performance. So this structure could be at different scale level. You can imagine this is a multi-scale structure, but what is the difference between property and the performance, right? In material science, people care more about property, but in mechanical engineering, we talk more about performance. And the difference is that when you talk about performance, the geometry, the part shape comes into play. Okay, so you're assessing a performance of a part, and on the other hand, the property is at a specific point. Okay, so from one location to another, the property can change because the underlying structure can be different, right? So this basically opens a huge design space. Now we can design process, we can design structure to accomplish very special property and the performance. So why my material science faculty are focusing more on what we call the forward analysis. Mechanics people are working on really assessing the impact of the structure on the performance, right? And the material science is more processing structure and property. My group is more design, computational design group. So we are focusing more on the inverse problem. Like given any desired, performance, how do we quickly go back to find a solution in the space of process, structure, to accomplish the property and the performance we want? Another reason to answer Professor Shearing's question, how I get into this area, is in the past decade, there's just so many research funding opportunity in this area. National Science Foundation, every agent, these are I listed the agent I have worked with. So there are a lot of projects funding projects related to new material design. So now let's talk a little bit about the design research topic. So I kind of view that this is a very multidisciplinary subject. And at the center, I'm putting data science here because that's what I actually like to focus on today, is how data science can help all this. But in the wheel, we are design engineer is working with people who are specialized in material modeling, mechanics, as well as manufacturing. So what are the special issues with design research, right? So I put them down into 3 categories: design representation, design evaluation, as well as design synthesis. So let me tell you a little bit more. I think the design, I see a bunch of design colleagues here. Those terminology are very familiar with you, right? We start by defining our design space, and then we evaluate performance. The synthesis is more like optimization, right? How do we come to the end of the solution? So what are the challenges? So the design representation part, the challenge we face is that the structure problem is very high dimensional. If you think about structure design, right, whether you should have material or what material at each location. So I'm showing 2 examples here. On the left, like in the middle of the one, this is more a deterministic structure. We actually designed this is the optimum architecture for a solar cell. Okay, so it can absorb the best energy. And in this case, the representation can be, we use deterministic representation. So you can imagine we can do a design on this surface, like do this grades, right? If we do 10 by 10, that's 100 variables. And if we do 100 by 100, then it becomes 10,000 variables, right? So the dimension can easily go up when you really look for very fine resolution. On the other hand, many of the material systems we work with, underlying structure actually is very stochastic, very similar like the feather of the bird I showed you, that if you look deep down into the material structure, they're called the microstructure. At the scale level of a nano scale, they look like this. Okay, so you really need to come up with representation for both. And also sometimes we're facing what we call the mixed variable situation. Some of the decisions we have to make, more like qualitative, for example, what kind of filler we should use for this composite. There's many types you can choose, and what kind of matrix you can use. There's many types, right? Surface treatment method. So that becomes, when we talk about design search, it becomes a combinatorial problem that could easily also dimensionality go up. And in terms of design evaluation, we're using a physics-based approach. So our simulation could be DFT, density function, molecular dynamic simulation, as well as finite element, right? So each simulation is taking days, hours, days. And so how do we use them for design? Because design optimization usually needs about thousands, at least thousands of function evaluation. So the computational cost, and what adds to this complexity is the multi-physics aspect, and as well as the multi-modal, meaning some information may come from experiments, some come from simulation, some come from sensor data. So how do we integrate all this together? So the last question is really the design synthesis. That is when we try to come up with the best solution, or what we call the optimal solution. So this vast design space, it could be also at multi-scale, right? We talk about the material system, they're always atomic, micro, meso, all the way to the macro scale. And how do we search solution at each scale level? Because each scale, there's some decisions that may be involved. And because of the manufacturing process impact, material is really heterogeneous. If you think about composite design, right? If you fabricate it, each location, the fiber angle can be different. That means the property can be different, right? So how do you take into account the process impact that introduced this location-specific property, okay? So how do you do that? So these are all the challenges. So what I show you today are the methods we have been working on is called the data-driven design. And we are combining both statistical inference technique as well as machine learning technique, like AI methods, that to kind of come up with we call the closed loop discovery that can help us to make wise decisions. So I have to admit that this is the talk I gave first time that I really are very ambitious, try to talk about 3 different examples, and let's see how it works out. So I want to start with example that is at we call the microstructure design with nano composite that has this stochasticity, then goes into architecture design. This is the thing you see in the poster. This is a heterogeneous architecture. Okay, so the architecture design is the focus here. And the last one is the most recent work on the programmable material design that has number 4 dimension. In addition to 3D geometrical design, now we are designing the stimuli that needs to be embedded, or the active material need to be embedded into the system to achieve different functionality. So I will mostly focus on the middle one and try to go a little bit quicker for the first one and the last one. So nanocomposite design, and the challenge that I'm going to address in this part are mainly the method we address, we call the mixed variable problem, the lack of data problem, as well as this multi-model, the information may come from both computer experiments and the simulation. And we have a method we developed about 3-4 years ago. We found this very useful. It's called the latent variable Gaussian process. So it's a statistical inference-based approach, and combined with Bayesian optimization, works really magically to find the optimal solution, use very small number of simulation and experiments. So I'm going to use this example called the multifunctional nanodielectric design, and the student actually already graduated. So it's multifunctional because for this kind of material, this is nanodielectric. You can imagine it's used in the wire, the electricity utility line, that you actually have this kind of material to achieve good electrical property. In this case, you want to have good storage, good insulation. And on the other hand, it has to be strong mechanically because the line has been there, sustained wind and those things for many, many years, right? So the endurance is also very important. So what are the design space? This is an overview chart that I'm going to go deeper into several blocks here. One challenge is the mixed variable nature, that we're designing both the morphology of this composite, which means really this dispersion of the particle has a huge impact on the mechanical property. You know, whether they should be far apart or very close to each other, strongly impact the material behavior. And it is also competing in terms of the mechanical property versus the electrical storage property. So on one hand, mechanical property, you want it to be more dense to kind of really like a reinforcement, right? When you add the nanoparticles, it makes structure stronger. But from the electrical point of view, that it really needs to be the dielectric point of view, that it needs to be really kind of far apart. So what is the trade-off? And the other decision include what filler. So there's two choice, PMMA and also PS. These are the polymer you can choose. And on the top is the different processing condition, like different surface treatment method you could use. So those are all discrete choice. And sitting in the middle, we have data from experiments. We also have data that we coming from simulation that use finite element simulation. And what makes it an expensive problem is that you really have to model the interface behavior. And interface means the filler and the matrix, when they intersect, there's actually a zoom that they're not this one material. Okay? There's a gradient property that follows. So you have to model those properties because it has a huge impact on the behavior. So finite element can easily take a few hours. So the approach we're using is, the problem here is really we really want to reduce the number of simulation. So we're using statistical methods here that start with the Latin hypercube design, very small amount. Then we create a Gaussian process model. And the nice thing about Gaussian process model is that you can view this as a machine learning model, but it takes very few samples. And one nice thing is it can model very highly nonlinear behavior. And on top of that, it also gives you uncertainty quantification at the location that you don't have any sample, because if you only have 4 data points here, right, there's millions of ways, there's infinite amount of ways that your curve may look like, all passing these 4 data points, right? So that means in between of those data points, there is uncertainty associated with the prediction, okay? So Gaussian process model give you the uncertainty prediction that can guide you to decide where do you do pick sample next. So the decision of where to pick sample is done by an acquisition function that makes a trade-off between further explore the space, like to reduce the uncertainty, or doing optimization just based on the current model, which may not be accurate model, right? So you kind of balance this exploration and the optimization, and the acquisition function allow you to decide which is the next point you should pick. So this process is iterative, so it goes through, oftentimes, this is one point at a time process. After a certain amount of, depending on your input, dimensionality, oftentimes you can find the optimal solution in less than 100 sampling for a problem, say, with like 5 or 6 variables. Okay, so it's very efficient in guiding the either physical experiments or the simulations. So the problem with this approach has been there, and there's actually a significant increase of interest in this approach, I would think, only in the past 6 years in the material science community. And I think 6 years ago, probably not many people using Bayesian optimization material design, but now you can see lots of papers are using Gaussian process for material design, process design, structure design. But what is challenging is that this existing method only works for variable, the inputs are all continuous variable, but they cannot handle categorical variable, like discrete variables, such as what filler to use, what surface treatment you need to use. So that's where the contribution of our research is about, is that we develop a method called the latent variable Gaussian process. And the key idea is that if, say, a problem, we have some inputs are x are continuous variable, and the t are the categorical variable. For each categorical variable, like could be different shape, right? Triangle, circular, square. We bypass the physical descriptor behind them, but we directly introduce a latent variable only has 2 dimensions. We found it's quite sufficient, z1 and z2. So in the Gaussian process model, the Gaussian process is based on the spatial correlation. So there's correlation function, and the hyperparameters are the sigma, and there's few hyperparameter, and the theta, which is a roughness parameter you need to fit. So in addition to those hyperparameter, we're introducing the latent variable as additional hyperparameter. So the maximum likelihood function is optimized by finding the hyperparameter value. So in this case, finding the hyperparameter of those qualitative concept becomes like considering by taking into account their impact on the property. Basically, this location tells how the 2 different qualitative, how the 2 different levels are kind of correlated with each other. So for example, if the solution at the end in this latent space, we found that the square and the circle, they're very close to each other, it just means that the impact on the property are very similar, or they don't have much differences. But when something like a triangle is far apart, then it means that the impact on the property is quite different compared to triangle and the circle. So to some extent, we call this interpretable machine learning because it gave us some physical meaning. And so there's several, like a key feature of this method I'm listing here. On top of everything, it is a way to kind of transform a problem with a qualitative variable to a problem with only continuous variable, because the latent variable are continuous. Okay, so our Gaussian process model is a continuous model. On the other hand, we build the surrogate of those qualitative variables by introducing latent variable. And the secondary, different from most of the latent variable-based machine learning, I think some of us are very familiar about, that is usually only deal with the input space. Here, it is a supervised learning that takes into account the relationship between the input and the output to find out the location of the latent variables. And it also provides uncertainty quantification that allow us to connect with the Bayesian optimization that I introduced early. So using this technique, this code actually was downloaded by many times, like in 2 years. The reason is because it's not only, I think, only for material design. You can use this method for other problems that you have qualitative variable or quantitative variables together, and you can integrate with Bayesian optimization. So this code is now being integrated into commercial software called EyeSight. It's Abacus. It's part of the Abacus suite that they're going to integrate this algorithm into their code. So let's talk a little bit about what are the continuous variable for this the dielectric problem. The continuous variable here is the design morphology. So instead of using treat the whole morphology space, which is very high dimensional, now we actually use a method called the spectral density function. That it's a Fourier transformation of this very complex morphology. So for this kind of shape, like the feather of the bird, you can imagine it's kind of like that. We actually found that a step function is sufficient. And this step function corresponds to, this in the optical space, it's like the ring, like a ring shape, right? So inner circle, outside circle. So for design, it becomes a much simpler problem that now you only need to design the lower bound and the upper bound of this step function, and you design your structure. Okay, so what matters is not this shape, but more like the morphology is really could be transformed into, in the spectral domain, into such kind of functions. So reduce the variables significantly. So for our problem, what we did, this is also related to processing. We asked our experimentalists in our team. This is DMREF project, so we do have people who are doing simulation, doing experiments. So they produced a lot of nanoparticle structures using the extrusion method. And we did image analysis, and we found that doesn't matter how you change your processing condition, that this could be the resulting microstructure. We only need a very simple spectral density function here with two variables in this case. One is the volume fraction, which is the proportion of the particle, like it could be 5% or 20%. Another parameter is a variable called the dispersion parameter theta here. And this two value, the one on the left, the theta is 0.51, on the right, theta is 3.11. With these two variables, we can come up with many different morphological design, basically. So this becomes a two-variable problem rather than such a complex morphology. So spectral density function works great for the morphology. And using the LVGP method I talked earlier, we also optimize what kind of nanoparticle you should choose as the filler, and also the surface treatment method, which is we have several different choices. So here is a single objective optimization for the nano dielectric, the utility Y problem. We have three different objectives, like the related to breakdown strength, permittivity. So we kind of give weights, right? Single objective is giving weights. So you can see the solution kind of, this is the starting solution, and it kind of converge to this is the optimal solution that shows that the best morphology, the theta this is 1.42, the volume fraction is 1.9, and then the filler, the best filler is the PS, and the best surface treatment methods is the amino. When we have multi-objective, we can also do, we call the Pareto optimization, but before I show you that, I also want to show you that the physical meaning in the latent space, right? Remember I talked about the latent space. For this problem, we found that the 3 different concepts of, we call the level, for the surface treatment, perfectly lined up well on just a horizontal line. So it basically means that in this case, a single-dimensional latent variable is sufficiently to explain the differences between these 3 different concepts. So we went back and we talked to the expert in the area, what variable you think that can really, a single variable. So we actually looked at a called interfacial energy descriptor for this 3 different kind of surface treatment methods. And then we look at for both the PS and the PMMA, and we found that the value of the this parameter interfacial energy description and the distance matches perfectly with what we observed in the latent space. So this is a kind of a simple example just to show that the latent space could be explained by some, like the physical phenomenon behind. But on the other hand, this kind of understanding this visually is really, really helpful, right, for us to think about, the differences between the different concepts. So for multi-objective optimization, what we did is that we looked at compared to genetic algorithm. So this is a GA. We all know GA is a very powerful method for global optimization. We found that with the Bayesian optimization is a much more effective approach to identify the solution. And on the right, I will show you the history of how the samples are picked. So you can see that there are 2 disjoint locations, like on the left and in the bottom. But those actually correspond very well with the 2 different polymer filler we have. So in the design space, because the introducing of the discrete variable, we actually introduced the disjoint design space. But with the LVGP approach I talked about early, now we actually come up with a continuous model, okay, underlying this disjoint space, which allow the Bayesian optimization to jump around. So if you look at the history, right, of the simulation, they actually switching between the 2 different domains. So the points, the sample can come either there and here based on the uncertainty, the acquisition function. And the green points here represents the different, called the Pareto solution, right? These are the solution on the Pareto frontier that shows a trade-off. So none of them are superior than the other unless if you give the right trade-off of the weights to the 3 objective functions that you have. So those are the best morphology on the frontier. Based on your real application, you may be able to come up with a good weights for these 3 different criteria, then come up with the best solution. So now we are moving to the second subject. I see I have already used quite a good amount of time. So metamaterial design. And here, actually, I like to talk a little bit more about this machine learning technique. We are also using LVGP in a way that it use it as a machine learning model, but this is the area actually the large, like some of the advanced like deep learning methods can play a role. And we are also looking at the data quality issue. So metamaterial system are architectural system that by manipulating the architecture, you can achieve different functionality. I'm including 2 more civil engineering related problem that you are manipulating this is the concrete. Like concrete has been made in the same way for many, many years, but now people are thinking about making different architecture using those material so that in the building on the highway, they could serve very well as the, for we call the oxidic metamaterial. This is actually not oxidic. The oxidic in the lower part, this is the kind of metamaterial actually can generate to do energy harvesting, So you can imagine that on the highway, people may be driving electrical vehicle can use the motion will generate the energy and use them to create the signals. So they could be used as a sensor in the building environment. But all these problems involve how do you deal with manipulating the architecture. So what we find is that most of the existing methods look at the architecture, like always try to use the same structure everywhere. We call them periodic system. But on the other hand, the system that we like to design, for example, this is a soft robots that can deform its shape. The best solution for this kind of structure problem is at each location, you want the strand to be different. So you want a heterogeneous property to achieve the function that you designed. So how do we accomplish this goal, right? Using the metamaterial system that traditionally have been always designed periodically. So we're coming with an idea of what we call the building block. It's like a Lego. So if we can create like a database for each different Lego that with property information, then we are able to retrieve those information and then design the distributed property as we wish. So that's the basic idea behind this methods for multi-scale design. And you can also imagine that this is a multi-scale problem because we're not only designing the shape of this butterfly, we are also designing at each location of this butterfly what should be the underlying architecture. So there is a multi-scale topology optimization. Nevertheless, the traditional topology optimization, like what I'm showing here, is a history of how you use topology optimization. You say, come up with a structure that can reduce the weight, right, when you apply the load. This is what topology optimization will tell you. But one big disadvantage of many of the current methods that you have to assume the material is the same everywhere, right? So now we have to come up with a method that we can design architecture differently at different locations. So that comes to the machine learning, the data-driven methods that I will introduce next. So here we have envisioned that there's several different modules. Start with a step. The first step is very important, is how do we collect data, so acquire. And then the next step is learn and generate, meaning that not only we want to learn the relationship between structure property, we also want to generate new, better design. And then the last piece is the optimization piece, focus on how do we integrate this data-driven machine learning knowledge with the topology optimization so that we can do multi-scale topology design. Okay, so that kind of using the data-driven method to kind of reduce the complexity. Otherwise, it's going to be a nested kind of optimization situation, higher scale, lower scale, a lot of computation. In this process, we also want to generate design rule. One thing is we're interested in, for example, is what is the interplay, right, between material design as well as architecture design. So the challenge here we're facing, so I'm going to walk you through a little bit about each of those blocks. The first block is really something that my group has really worked a lot these days, is really the data quality issue. If you think about machine learning, right, if you start with a data that is biased, you are not going to get a model that gives you the complete picture. So how do you create an unbiased model? And we're thinking that we can actually, there's a lot of different existing design, right? Unit cell design, like here I included the spin nodal structure, it's developed by Professor Karos Patel's group, and some other lattice structures. So in the design domain, they may be sitting at a different location, right? They are multi-class structure. But in the property space, there could be a lot of overlap, right? And then some of those may accomplish the same objective because design is never one-to-one. It's always one-to-many mapping, right? Like one target, you can come up with many different solutions. So the question here is, can we really build a unified space for multi-class unit cell structures so that we can kind of maneuver around in between those different class of material and maybe come up with something that is not like a dog and not like cat, but in between, right? And then here is the other question is really a challenge design question, is how we go beyond okay? Because we cannot be satisfied with just the existing the data we have. Oftentimes, our goal is at a location that is far away from what we want, right? So this is a paper that my student Dokso, he's close to finish his PhD here, that he developed this called task-aware data acquisition, giving a large sets of data, but it's called unobserved, meaning that in the geometrical space, we actually can have lots of data. Here, we can have, like here, as example shows, close to 88,000 different geometry, right? But we don't know what's their property, and that needs to be simulated, and that's very expensive. And in this case, for the material design, oftentimes we're looking for some very special property. In this case, it's called anisotropic sample, meaning that C11, C22, these are the different tensile components in the material property space. We want them to be like the ratio as high as possible or low as possible. We don't want them to be sitting on this diagonal line, right? We want them to be at the other edge. So here it shows the algorithm. Basically, I'm not going to go into detail, but just to show that this is an active learning approach, that we start with a small sets of data, but we gradually decide how do we add samples so we can pushing the data to the location we want. And you see an envelope here because there is a physical limits, right? There's a space you can never get to. So to some extent, this also gives us identify the physical boundary of how much we can accomplish. So on the right, you see this is the distribution of the property when you have a random, like a randomly sample anything. And we combined the idea called the diversity matrix. That work was inherited from the work that Faiz was doing in his PhD, coming up with a way to assess diversity of different design in a very quick way. So we're using diversity. We're also using, we call the task-driven. So in this case, we have an objective that really push the points to those locations that we want at the two different ends in this space. So it's not going to be a unimodal, it's going to be two different peaks there, right? But that's what we want. That's basically we want the data that coming to the bounds. So once the data is collected, how are you going to use this data? We actually build a system, and I will show the address a little bit more clearly later. So it can take different data sets. So the orange one and the purple blue one may come from many different kind of lattice structure. And we can actually maneuver around. And when you maneuver around, you see the design. And you see their Young's modulus, you see the Poisson ratio. And at the end, you also can find in a reduced dimensionality space, this is called the UMAP, reduce a 6-dimensional property space to 2 dimension and identify how close different designs are based on the distance in that space. Okay, so this is some of the, we call the deep learning technique that can really do this latent space to identify the distance between very high dimensional attributes. So this is a tool that we just developed that we hope more people will contribute to the data and use it as an interactive way. One interactive thing that this can help is you can look at in the small neighborhood, right? Two designs are very close to each other, but they could feature what kind of common feature they share and why they're close, right? You can look at the geometrical feature and identify some reasoning, some physical interpretation behind them. So now with the data, now we can do machine learning, right? So there's a paper that my group recently, we actually took a year to finish this paper because it's a literature survey paper that just recently accepted by Advanced Materials. So it's still in press. And we did about, I think, more than 300 references in that paper, looking at how people use data-driven methods for metamaterial design and the multi-scale design. And what is interesting here is we put them in the different category. Some of you may have seen this kind of chart before. It shows like a different kind of physics. For example, it could be optical system, acoustic, mechanical, thermal system. And this category shows some of the method does not need any iteration. So it's called iteration-free to get optimal solution. Okay, you know some of the machine learning technique, right? Now, giving the targets, and they can tell you immediately what is the solution. And some of the other methods need iterative design optimization. And this is the column shows some of the different one-to-many mapping or direct mapping or cascaded neural network. And the last column maybe is the most interesting to some of the students here who are trying to figure out what is the machine learning technique that could be useful. So in this case, you can see like the GP model I talked about early, there are not too many papers, but on the other hand, DGM, I think this is the generative modeling approach. That is one popular one that actually could be used for both forward prediction as well as inverse design. So they can do optimization without any iteration. Giving a requirement, it will tell you the solution right away. So to some extent, the generative model is very useful for very complex geometry. So if you're interested in complex geometry, this is a great method to use, okay? But if you're not interested, if you're just going with simple geometry, you probably don't need this technique. So what is happening here is that it can create a machine learning model based on geometry and property data, and now you can use it to create a new design at the property that you want. And they could be very complex geometry. So there's an encoder and a decoder. So the inverse design, you only need to tell what is the point. So generative method, if you tell what's the target in the property space, using this generative model would give you directly, there could be maybe several different solutions that all achieve this target. And on the other hand, the traditional iterative method, it will need to take the optimization, multiple function calls in order to converge to the solution. So the same method can be used to model uncertainty. We actually have manufacturing induced imperfection in geometry. We could actually learn data, multiple parts, and this is a hierarchical generative model that can now, in the future, when you do design, you do a nominal design, but it could also automatically generate what is the imperfection, okay, of your parts based on the existing data that they learn from the current manufacturing process. So this is very handy for robust design or optical metamaterial, which is very sensitive to the geometrical imperfection. So this is a hierarchical generative method. Now coming back to this, we call it the multi-scale design, right? I talked about very early that we want a distribution of a structure at a different location. So how do we accomplish that? We're using two different strategies in design. One is called top-down, one is called bottom-up. So the top-down method actually starts with a structure and then identify the ideal property distribution rather than the ideal architecture. And then retrieve the database to find design that are compatible, that can form this kind of meet the distributed property. The bottom approach is different in that we are first starting with the data, then we create a machine learning model. It could be GP model or generative model, then pass to the higher scale level topology optimization framework to identify what is the optimal solution. So it doesn't really optimize the property. It optimizes the structure directly, but it uses the machine learning model as a surrogate so that you don't have to have this nested situation. So both approaches can work well for certain problems that we say homogenization theory is applicable, which means you can passing the information from one scale to another in this kind of way. But for some highly nonlinear problem, it may not be applicable. So here I show you two examples. This bottom-up method, we actually used this approach to design a compliant mechanism that you start with a block. You don't know how you should arrange your material. And at the end, we have two choices of material. One is hard material, one is soft material, and each of them has 8 different architecture, different kind of a lattice structure. So we build a machine learning model ahead of time using this LVGP method I talked about earlier that treated the different kind of architecture as a category variable in this case. So then we use this machine learning model on the top level for topology optimization. So you can see the solution here converge nicely, like to put very strong material at the hinge, right? and then to use the soft material, not strong material, at some other locations. So actually the soft material here at the hinge, the harder material, the stiffer materials are at other locations. So a real life example could be something like a doorknob, right? You designed the architecture. So the latent variable space that I'm going to go there, it's very interesting that using the data we create, we actually can see in the 2D and the 3D lattice structure, we can see what are the concepts that are very close to each other, meaning that their properties are very identical, and what are the concepts that are very far apart. And they make a lot of sense to us, right, in terms of their impact on the property. And then with this technique, we could also do, we call the functional gradient structure, because from the manufacturing point of view, you don't want the architecture jump from one location to another significantly. So you want some kind of algorithm that can do a smooth transition. So we use both that we call the blending methods. It's a numerical technique that can blend the different architecture, like several different classes, into something in between, but still connected. And we also used this deep learning method. So this is the nonlinear manifold learning. And you can see that now with this generated model, right, we can work from any point to any other point in this space that can come up with the corresponding geometry. And those geometry, because you're walking along the line, it means that they're very well, they could be very well connected, okay, from one to another. So that's the idea behind this functional graded kind of a structure that using this kind of database and the generated model. And there's some other numerical methods we use to making sure that there could be an angle. So we're introducing the called the sawtooth function to do the transformation. So we could design architecture not necessarily has to be vertical. It could follow some kind of angle. So the structure could be close to the, if you use topology optimization, you're going to get a very similar result. So for the work that you see on the poster, it is actually done by a top-down strategy that we first design the optimum property at each location, and then we choose what architecture is the best. So this is a shape deformation example that the crying face can become a smiling face, right? When you apply the load, you actually can see that it's the same architecture, but now it could have a very different functionality. So the string cloaking example, I will just kind of skip through this because there's some details that I'm afraid I won't have time to cover. But it is a strategy that decomposes the design variable into two sets. One is topological decision, whether we should have material or we have no material. And the other is the property decision, like what kind of property we should have. So skipping through this, and then related to the civil engineering application, here we have a example we designed for maximize the fracture resistance. So you can see that compared to using periodic structure, using a heterogeneous architecture, you can achieve much better resistance to fracture. So this curve here, it can go further along in both this direction, as well as the total surface like area integration value is much higher than the other two curves. So from the fracture resistant point of view, this one does much better than the other two design. Now with the, I will just use 2 minutes to talk a little bit about the programmable material system. So in general, the programmable material system, really the complexity, my group started to work on this about a year ago. What is the really challenge here is that it introduced the dynamic aspects into the problem, because now by creating, like introducing like a stimuli into the system. So when you do 3D printing, you're not only just print the geometry, you also print the material that can respond to either light or other source like thermal source, or there's several different stimuli that you can use. So this is, some people call this 4D printing, right? And to some extent, you can think about that you're creating a coding, like in computer science, that you do coding. Here we are developing a program that we can deposit the right stimuli at the right location. So now when we have the external stimuli, it can behave in the way we want. And it's dynamic because it's not single state. There are multiple states that are multiple desired shape or functionality that you want to achieve. But your design have to be one single solution, right? So I'm going to skipping through some of the details of the fabrication, but thank for the people who works in manufacturing as well as in mechanics. So their Professor Xuanhe Zhao here had this process, right, called the hard magnetic soft material process. This project that I will show you is working with his former postdoc, Renee Zhao, now is a faculty at Stanford University, that we use this printing process that we can now print a kirigami system. So the design decision here is how we cut this a sheet of paper maybe, but now it's a magnetic sheets that then at each location, what should be the direction for the magnetation, okay? Because you can also fabricate them in the different dimension. So very high dimensional because each of this element we need to decide the location, so the shape, right, where to cut, as well as the direction at each of this element. So now we are getting into an area that quite exciting that I see some other groups are also using this for dynamic system. It's called the differentiable design. Okay, so we are using a differentiable codes that can calculate the gradient. There's automatic differentiation it does, so you don't have to do analytically at different location. And this is the physical validation done by Renee Zhao's group that what you see the movie, it starts with this geometry that you just decide where to cut, and then it can deform into the desired shape. So now we have a code that you can tell me you want a sook, like this kind of egg shape or heart shape, that we can tell you the solution in just minutes, okay? That very quickly, it can tell you what's the best solution. So in terms of where you cut and the direction of the embedded magnetation at each different locations. And to make it multiple state, it means that you want this thing can evolve into different shapes. So just with a differentiable algorithm, it becomes much, much quicker to find a solution. So here is some of the ongoing work that people ask me, like what makes you excited these days that my students are working on. So for the metamaterial system, we are also working on optical system, which we can't really use the homogenization assumption that I showed you early, passing information from one level to another. We have to study them all together as a whole system. So we're using neural operator that can learn the inputs here. The design space is both the geometry, the architecture, as well as the phase diagram, which is the external stimuli that you apply. So both are fields. And then output is also field. And in terms of the optical property, it's very tricky. The desired property is usually some concentration at the different peak value at different location. So again, it's very highly dimensional. So neural operator is a method that works perfectly for this kind of scenario and also for design purpose. So my student is presenting this in next week, the SES conference. So that's Doxo's work. And on the left side is Li Wei, who is a postdoc, has been working with me for multiple years. And he's looking at this kind of networked system that can do shape deformation as well as mechanical computing. You probably heard about this concept using mechanical system that giving some kind of signal, it can create different response. So it used the mechanical system serve as an actuator. So in replacing the commonly used like a computing system, which is analog and some other system, that here we're using, we try to use a mechanical system. So the thing we play with is each of those links can have different material design in terms of stimuli, because it can be like extend or can shrink, depends on the external condition. It could be thermal or light controlled. So design decision is associated with the architecture of this network, as well as each link, what material you're going to put. So this is really a combined material and architecture problem. It's a great example to show how we can do both simultaneously. So with that, I would just close by just highlighting a few key things. I'm not going to read all of them here, but what I want to emphasize is that from the design researcher point of view, the design representation comes out to be actually a very critical aspect, like in the how do we describe our design space in the way that has the smallest amount of variable that we can solve. And the design driven methods of machine learning is really becoming one of the key topics these days. We call it AI for science and also AI for design, right? That it comes together. In this process, and my group has been very interested in this question about data quality. How do we really ensure the data has a good quality so it can really describe the phenomenon correctly as well as giving us the right direction. So with that, I really like to thank Phil, the funding agent who sponsored this work, and this is our family picture for my group. So thank you.
Thank you so much, Wei. We have time for a couple of questions.
Yeah, I hope I didn't overwhelm you. Really, lots of information. Yeah.
Great talk. A quick question on, you mentioned it briefly, so the nonlinear response, of course, very challenging.
Yeah.
But how could we potentially overcome that?
Yes, yeah. So I think for the multi-scale approach, I feel it is still hopeful. That's something we want to test with some of the nonlinear constitutive relationship comes in. We actually like to start with a linear solution. So there's several strategies with that. We start with a linear assumption. We figure out like a starting point for design, and then we keep refining it. So whatever there in the topology optimization field that deal with nonlinear problem could be borrowed here. But we need to have some revision in terms of how do we address this multi-scale aspect, because the conventional topology optimization nonlinear problem is usually single scale. So I think that there's a hope that combine those methods together with the data-driven methods to really shorten the time to accomplish the goal. Yeah. So, but that's what we want to work on next. Yeah. I see a couple of hands. Yeah.
Hi, great talk. I just had a quick question. You mentioned early on about understanding the latent space and how there was an interfacial parameter.
Yeah.
I wanted to ask, how did that link come together, or how did you discover that there was a link there, and why did that possibly connect to what is happening in the latent space?
Yes. So I think it's not an explicit link from the viewpoint that we're not doing any machine learning like between the latent variable and the descriptors. So let me quickly go back. I think this is probably the slides that you ask about. Is that like how do you connect, how do you identify the latent variable and the?
Yeah, but I think the one slide that popped into mind was when you said that it was like an interfacial energy parameter.
Oh, yeah. It's a good question. So we never know what is behind. So, and in this case, it happened to be that it could be narrowed down to this single variable. So when we see it is sitting perfectly on one line, it just tells us one variable will be sufficient. One physical descriptor will be sufficient. And then we go ahead to talk to the people who are specialized domain expert, and we discovered that it's it matches well. But in other problem, when you have, like, they're not in the horizontal line, it's not easy to explain how many variables behind. Like, then it could be 6 or 7 even, right? So we actually have a student who did expanded the LVGP to descriptor augmented method to deal with many level problem. Like, there's some problem with many level. We actually have another machine learning going on to fit some relationship of the physical descriptor with the latent variable. and they help to predict the relationship. So there's another kind of a neural network inside you can build to accomplish that goal. Yeah.
Nice to meet you again. Last year you visited University of Pittsburgh. I was there.
Oh, okay. Did I give the same talk? No, I don't think it's the same. Yeah, I tried to make a different talk. Yeah. Today is more impressive. Oh my God. Okay.
LVGP.
Yeah.
I have a question, like, does it fit the data, which the data pretty like expensive, or because we cannot trail many data, we want exactly find the data before we testing the data is bad.
So LVGP is great for small data problem because it can combine with Bayesian optimization. It has this uncertainty information. So we actually use LVGP for small data problem that you cannot collect lots of data. But on the other hand, all the GP model, usually people ask me how many variables you can comfortably deal with, right? I think under 20 variables inputs would be very powerful, but when you have more than that, then we have to create more data and fit the GP model, and there's some technique actually. In order to get better GP model, you have to do some statistical work to reduce the amount of data, because GP behind the scene, there's a inverse of the matrix computation. So it's a little bit concerned with the large number dimensionality. Yeah, but LVGP is great for small data problem. Yeah. Yes.
Thank you so much for your talk. Can I ask about your comparison between Bayesian optimization and genetic algorithm? Mainly because, to my understanding, two methods are relatively different. So how do you know that you're comparing them in a fair manner other than having the same number of maximum function evaluations?
Yeah, so here we say we do 100 function evaluation, that we are able to find the optimal solution using Bayesian optimization, but genetic algorithm is not able to do that. So genetic algorithm needs usually thousands of function evaluation to find the solution. So they're both for global optimization. Faiz, yeah.
Just a general question, like thinking about the work around data-driven for material design, what are your kind of thoughts about other domains of design process you can learn from your lessons around material science, and especially data-driven methods?
Yeah, so the work I talk about is very much what we call model-based work, right? So you have the physics-based model so that you have some property performance you want. It's not restricted to material design. I would say we actually work on Bayesian optimization for many other problems, so they're very useful. But on the other hand, design is not only just using model, and there's a big part of it is conceptual design, coming up with the concept, right? So for that part, actually, I really like the work from your group that this morning we talked about your group work for, you call the multimodal. So you have both text as well as image, like a sketch comes in. I think those methods will be very helpful for the early stage design problem, but they also use generative model, right? So I think it could be used, like the approach I talk about could be used in the little bit later stage, but the approach you talk about could be used in the early stage. Yeah.
I was curious if there were some lessons from this which you think can kind of transfer to other stages.
Transferability, okay. I think right now the work we talk about is still very much like parametric based, I would think, right? So I think, as long as the problem fits into that, this approach will work very well. But in terms of the lessons learned, that's a hard question. Faiz was my postdoc. He asked me, he challenged me. What is the lessons learned from this process? Any specific thing you want to know? I think you may have some specific thing you.
I feel like a lot of the things which you're talking about is like very relevant for like other people in the design who benefit from it.
Yeah, I think it's not lessons, but more about like in order to do well in this research area, we have to keep up with what's going on in the computer science area. like, you know, like in the, for example, the machine learning technique, generative modeling. We start with VAE, right? That's our earliest paper. It creates very low quality images, and then we move to GNN, again, at better quality, and now we are doing, we call the flow model, right? So all these things are becoming better and better. So there's lots of technique, attention mechanism, blah, blah, in the computer science area that very useful for some of the problems that we have. So I think there's a great future of the people who work in the physical science domain, like mechanical, material, civil engineer, to use data science method. But we have to know like what's going on, you know, in order to do the right job and use the right technique. Yeah.
With that, I think, unless the last question? Then I think if you please join me in thanking.
Thank you very much. Yeah.